Hello and welcome, viewers, to another Tutor Wizard stream. We are jumping back into the history of math today, and I think we'll be starting with the Greeks, actually. So, Adrian, if you could, here you are.
Take it away. Okay. As I take it away, we're gonna
Never
set.
to beg.
Yeah, yeah. Okay.
Well, we already have three viewers. We got to get one. We got to get to 290.
Get one in there. Okay. Yes. What Tim said. If he doesn't have a microphone, I've got the microphone. You shut up back there. Let me get the Mancala ready, and then I'll pitch it while we get Mancala ready. Ooh, that was loud. Sorry. What does the YouTubers, all the online guys say? Sound warning. I just slapped that closed. Okay, yes, what are we at?
286.
Followers on Twitch. So we have 886. We're trying to get to 300 and screw 300. We want 400. We want 400. We want a perfect square. 400 happens to be a perfect square. You tell me what the root of that is. Oh, why is this breaking? So I'm going to transition from, why am I not on Stream Manager and I can't see anything? Just a second. There we go. Two viewers. We lost one already because I started pitching it. Oh, there's four. I got to up. There's still four. Mine's slow. I'm updating.
If all four subscribe, we get to 290 today.
How come some mine says two? Yeah, and then if all four of you please subscribe, you're like, I already did. The dedicated ones are already subscribing. But we're going to transition from the end of Egyptians to the Greeks. And then when I taught it to Lorenzo, that's where we ended, was in the Greeks. I just spent all the whole time in. So when you hear me saying it's all Greek, to me, it is not. It is both literal and figurative. Literally. So I have an actual version of Mancala, and this. Oh, and it even looks like the picture in my PDF notes that when we send it to you, I bought one online. I was like, hey. I looked at the picture and I was like, I want one of those, and then I ordered it online, and now I have no money. And it's because I buy things like this online. But what they were doing is, can you see what they're going to do here? This is a game, and I can't remember what the game is. You can move one, two, or three, and then you have to get all your guys in the Mancala eventually. But that's not why I want this. I can ruin games with anything by using math. And what the Egyptians did, so we'll do Egyptians and then we'll do Greeks. But the Mancala, let me spell it correctly. Womancala. Whoa, Mancala. So Mancala is this game, but what they were doing was they were hollowing out with circles, and then they were putting little pebbles into there. But the pebbles make a square. And then they were like, ooh, I could probably approximate pi with this business. And so this is a way from playing a game and sitting there days in and days out. There was no TikTok or Twitch or anything back then. So they're looking at this, and what they would do is they noticed that the pi r squared was approximately equal to x squared, if you called that the x and then the pi r squared. So they're going to get this. And then from this, they could immediately get that pi was approximately equal to x over r squared. And so the one that they used was in that, and I don't know where it went. I was like, where's my rind papyrus? I put it somewhere. I took it upstairs. I don't know what I did with it. But I have a whole bunch of Egyptian stuff. I have a sarcophagi with the mummy inside.
You need more hands.
I know. I was like, I need more hands. And then we've got the Sphinx. Whoa, easy Sphinx. We've got the Sphinx, and then we've got
Your extra set of hands is coming.
Your extra set of hands is coming. So we've got a ton of Egyptian stuff, and then I don't know who this one is. I think that's supposed to be Nefertiti. Nefertiti. What? Oh, it's signed by the guy on the side.
I think there's something to do with Nefertiti's eye there. Is there like two different eyes or
Yeah,
something?
yeah. There is. So it's Nefertiti. So yeah, one's carved and one's not. You're right. Good. He knows history better than me.
So on the topic of bad jokes, you can't say sarcophagus without coffee.
Yes, and he can't.
Yes, it's a bad joke.
He wouldn't give it to me back, and I dropped it, and it broke. Give me that. Anyways, I got a bunch of Egyptian stuff down here, but one of them is this Mancala game, and using X is 3 because they were using. Oh no, what did they use? I'll use the rind papyrus. So from this rind papyrus, I need a new pen too. That one's almost dead. And the kitty disappeared as soon as the Twitch stream. We've got a new black cat, which would have been extremely useful for the Egyptian cat that we have, but there's a new cat member in the family, and his name's Pepperoni. Pepperoni, even though he's all black, because they wanted to call him Pepper. But Mabel had a cat, Pepperoni, but she couldn't say pepperoni, so she called him Peccaroni. So I'm going to secretly call him Peccaroni. His name's Peccaroni. I'm calling him Peccaroni for the rest of his life. Peccaroni. I'm going to put these on the floor because they can't. The floor is a giant shelf at ground level. All right, from the Rhine Papyrus, what they used was pi was approximately equal to 8 over 9 over 2 squared. So they're using the R as 9 over 2 as their radius, or 4.5, and then they're using the 8 guy as the Mancala, the big man, probably the village Mancala ones that they had, etc. And then we're squaring this. So then if we do this, how do we do this? Now we have to, but notice also what we're doing here is irrational numbers. One day we'll prove that pi is irrational. This is a tour de force. But this is an irrational number, and how do we approximate, or the decimal expansion of these irrational numbers? We're going to go into a whole, basically, everyone views this, and I want to turn this around too, that after I get the coffee frog out of my throat. I got a frog too. You think I don't have frogs? Here's a frog. This is one of the plagues that they had. It's just the toads and the locusts. It's like, you've got everything down here. Yes. But we're going to do, everyone says these are grade school calculations or adding fractions and these types of things. But these are the tour de force to find out what the decimal expansion of a transcendental irrational number is. Also, I'm going to use successive approximation of rational numbers. So this is, now we have to add and multiply and divide rational numbers possibly. So what do we have? This is going to be 8 over 1 times 2 over 9 squared, which is going to be 16 over, oh no, 16 over 9 squared. Yeah, that's right. The math checks out. And what's that? 16 squared is going to be what? Do you want to do the algebra? Watch, I could do it this way. Instead of doing the 16 and saying, what is 16 squared? It's 16 times 16 is 256. But the way that we could do this is 16 is 2 to the 4 to the 2. And 9 is 3 squared to the 2. And then we're going to get what? 2 to the 8, which is 256. And 9 to the 4, which is 81. So it's all just successive applications of the exponent laws and the fraction laws, etc., etc. And why is it that we can do this? I have 8 over 9 over 2. Why can you just flip and invert it? Really what I'm doing is multiplying by 2 over 9 over 2 over 9. It's the same dirty trick. Cancel, 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 cancel. Oh, then I get what I want. So a rational number divided by another rational number, you say you flip and invert it. They say A over B divided by C over D is a bad notation. And what is that going to look like? In our fractions, that's going to be like this, C over D. But then how come you can just flip and invert it? Stop memorizing it, rememberize it. You multiply by the guy, the opposite of what you want, as in the form of 1. Cancel, 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 cancel. And then we get division is you flip and then multiply straight across. This is AD over BC. There we go, for all of them. So all these grade school rules are going to be used to flesh out the approximation of pi. And now what's this? Now we're going to do this one too. Because what can we do with that? What was that? Pi now was approximately, how good were they? It was approximately 256 over 81. Everyone pulls out their calculator. You've got one. It's wet in between your ears. Here's 256. And I'm dividing by 81. So what are we going to want? We're going to want the multiples of 81. How do I do that when I don't know? When it's small numbers, it's not so bad. But even counting by sevens, can you count by sevens, Tim? 7, 14, 21, 28, 35, 42, 49. It's harder than it looks. I practiced that one. I couldn't do it about a year ago. I couldn't do it. It's like 56, 63. I don't know. So this is hard. So, but what you do is multiplication is addition. So you just add it to itself over and over again. That's times 1, 81, 2. Now I'm going to make mistakes. What was that? 16. So then that's times 2. I get another 81. I get a 3, 14, 243 times 3, 81. I get 4, I get 12, I get 3, 324. That seems right. That's times 4. I cheated and I know I need up to 6, so that's where I'm going to go to because I've already seen this. This is a 5 and then a 10 and a 405. And if it's divisible by 5, the last digit has to be a 5. That makes me seem like I haven't made a mistake yet. That's how I check because I'm not confident in my adding skills. This is 6, 8, 4 times 6, and then the next one would be I ran into Mario. Luigi, I'm a little Luigi. Luigi can go here. Everybody else, get out of the way. We're doing math. Get out of the way. 81 is going to be 7, 16, 5, 67. That's times 7. The 7s are hard to find. Oh, I like that there's a 7 in 5, 6, 7. That's what I took from this. That's what I took from this. That just satisfied me. It's like, okay, we're done. Show's over. I just found out there's a 7 in 5, 6, 7. That's all I needed for today. So what you do is you approximate in some way. What they did was they were playing a game called Mancala, and they realized that they could form a square of pebbles inside an already rounded, hollowed circle that involves pi, because pi, I'll remind you, is the ratio to circumference and diameter in any circle. So pi by definition is a geometric ratio. It's equal to circumference over diameter, and diameter is 2 radii, and this is where you get the first formula from the definition of what this pi guy is. The circumference in any circle is always 2 pi r. And then what we have to do is find out what pi is, and then you can have the circumference of any circle you want. So what they're doing is approximating this using this game, and someone had the epiphany that they were like, oh, there's a square, and then this is what the Greeks are going to do. They're going to circumscribe. Don't circumscribe me. What if his definition? What if, I'm just thinking of Michael Cera and Jack Black in Year One, and he's like, they're gonna cut the tips of their penises off. What if his definition is different than my definition of tip? And they're all worried because it's the first Jews Year One. Circumscribe, inscribe. You want to be inscribed, not circumscribed. Circumcision,
immortalized on
just like peace. And that's why I was like, we need to bring Lorenzo. This is rated G. It's rated G. We're gonna get a meme where it's just Lorenzo swinging a stick at us, saying this is rated G. I want money, you idiots. And here's Bastet, the Egyptian cat god. That went in my mind just now. Anyways, we're going to do long division. I didn't want to do the long division. But what you're asking yourselves is exactly this. And then we want decimals. So we add decimals. Now, I'm not looking for the quotient or remainder. We'll talk about why this dirty trick happens a little bit. But as I do this, the first thing I have to ask myself, which you didn't ask yourselves, and hopefully it's... Let me ask it this way. Does everybody know that pi should be, because it's right above me where my hand is, it should be approximately decimal places, because that's as far as I'm going. ... So that's the actual answer now that we have the curse of knowledge, and it's right above you if you pan. Lorenzo lowered it a little bit, but I'm pretty sure you can see it right there. And I like the fact that somebody was smart. Tina bought the one that said approximately, because you can never write down as decimal expansion. So that makes me happy. And then what are we going to do? We're going to use, what I'm saying is you have to use logic. When I calculate the mass of an electron and it comes out to 3 grams, I think I've done something wrong and I didn't carry a 1 somewhere, because it shouldn't weigh 3 grams. So I use my logic to realize that my calculation is wrong. So what should the first number be here? If there's going to be any justice in the world, whatever this approximation is, if it's reasonable, this should be a 3. And it is. But what you're doing, and why you didn't like long division, was because you never asked yourself to take the time, and you're like, why is he doing this and he's taking so long? Just get to this. This will make this so much faster, because what you're asking is, what's the largest multiple of 81 that doesn't go over 256? And there it is right there. Now I have the multiple and the outcome. So I put the 3 and I put 243 below it. Bang. The decimal is going to stay there. And then we subtract. Oh, now I have to subtract. Okay, good. They're all larger on the top. Yeah. I don't have to borrow. 3, 1. I think I did that right. 130. Then I asked myself, how many... 162 is already too much. So this is going to be a 1. That's also good. And then did they get it correct? No, they didn't really. But we already have the outcome. That's going to be 81. Uh-oh. Now when the numbers... I don't have enough 1s, so I have to borrow 10 1s from this guy. and that goes to a 2, and then I get 9, and then I have 2, and that's not enough 1, so I borrow a 10 from that spot, and then now what do I have? 12 is 49, and then I bring a 0 down. Always, I'm bringing the zeros down, and then 490 is going to be 6. So to 2 decimal places, they got that this is approximately equal to 3.16, or if you do the long division, this is 3 1/6 as a mixed fraction. They liked mixed fractions, and they liked to have the, what did they call that? The unit fraction. So this is 3 plus a unit fraction, which they also liked. We'll get there, but the square root of 10 is also 3.16, which is fairly good. This is from India, I believe. So this is an approximation. So there's the segue from the walk like an Egyptian into where Herodotus was the first to say that modern Euclidean geometry and Greek geometry came from the Egyptians, from doing calculations like this, and they were called rope stretchers, because every time the Nile, I'm in denial, but there was also, Burhanadin's here. Hey, nice to see you. We're going to do a regular series now that all the cats have gone to play, and summer in the Hamptons. I have to teach 4 classes in spring, but we're going to do a regular series on Twitch, and then in the summer, in July, August, all I have to teach is Monday, Wednesdays in the afternoon. So we're going to start coming harassing you at... the real question is, am I a perfect square? No, I'm curvilinear. I hear that cat, though. I heard that cat. We will do perfect squares eventually. But for now, what are we going to do? We're going to segue into Herodotus. I don't know if I spelled his name right now. I think so. What he said was that there was, every time the Nile would flood, it would ruin part of the landowners' properties, and then they would have, we could even do this in color coded. We'd have the Nile, and so the Nile would flood this extra part, so it's flooded their land. And then what would happen is these guys would have their plots lined up, and then he's like, well, this is not fair. You're going to tax me on this land, and the Nile just took this part. So they would have to come out there, and as tax collectors, they would have to calculate how much area they've lost, etc. And this is the foundations, they believe, of the hands-on practical applications of where you get this abstract algebra, etc. from the game. But the real way we get geometry is, that's what geometry means. Geo is earth, and metry is to measure. So this is literally earth measure. And I didn't spell measure right at all. That's okay. I'm going to do the rest of the math will be solid. My English is subpar. That says measure, I think. But geometry literally means earth measure. This is what we're going to do. And so Herodotus sees this, and he brings this to the Greeks, and then the Greeks take off with this. And what the Greeks are doing is, they're going to start with Thales, I believe. Thales. Where's my notes? Did I lose my notes? I lost my notes. Kitty, come back here. We were going to tell you about... No, he ran. He doesn't play. I'm going to go catch a cat. So what was I doing? Werner Heisenberg has a quote there. Okay. I don't want to do that quote there. I was going to segue into this. First of all, I wanted to talk about the 3... There used to be... So Thales was quite the guy. He's like John Napier's spirit animal, probably. Because Thales was the crazy Greek. And what he did was he had to travel, and Eratosthenes does this eventually to get this circumference and radius of Earth, having never got off of it. And what he does is, there's Syene, I believe, is a city, and then Alexandria, where the first library of Alexandria is. And then what they're doing is, this S is 500 miles, I believe. And then what he does is he looks at what I'll tell the Thales story at the same time as the Aristophanes story. So what Aristophanes is doing is he's looking at the sun rays go down the well. And then when he sees this, he sees that when he gets here, there's a 7.2 degrees separation from this. And then what he does is he uses parallel lines and the center of the earth, and then he can get the radius and then the circumference of this, all from the fact that this has to be 7.2 degrees also. And then we'll do this next time when we do this, and that'll get you to come back. But next time I'll actually do the full calculation of what Aristophanes does. First of all, this is abhorrent to me, but this is what the Stewart calculus put it in, because it can't be in radians. Anytime you do any of these things and you measure in an actual circle in the real world, you have to use radians, not degrees. This is from the Babylonians. The Babylonians really like the fact that in a circle I can cut it into the 6 roots of unity, and then I can cut this into 60, and 6 times 60 gives me 360 degrees in one full revolution. But from the definition of what the Greeks are doing, the 2 pi, one circumference of the circle, if the radius is 1, is going to be exactly 2 pi, so this equals 2 pi radians. And so we're going to use radians. So the first thing I'll do is the red showing up. I shouldn't use red. I won't use red anymore. It's not terrible, but I won't use it anymore. So that was just a tangent to what, and then we'll keep the picture. That was what Aristophanes is doing. We'll do the sieve of Aristophanes eventually too. What Thales is doing is something much more practical. So Aristophanes abstracts this eventually, and do you notice that it took him over a year to do it, because this is back in 200 BC roughly, so he had to travel in between there. And what Thales was doing was salt, the pillars of salt, and don't look back, otherwise your wife will turn into a pillar of salt. But the major commodity is salt for everyone's preserving fish, especially in the Greeks and all these islands where that little Italian boot is. Everybody wanted salt to preserve everything and to make their food taste yummy. Yummy is the science word for it. So Thales has to travel from Alexandria to Syene, and he would use mules to transport the sacks of salt. And he had an Einstein mule that realized when they crossed the river, if he would just hang out in the river would dissolve a lot of his salt, and then it was much nicer on the second half of the trip. So then, to punish this bad, smart donkey, he would, on the next trip, he put rocks into the thing instead of salt, and then the donkey would get in his mind that it's not working anymore. And
Punishment for being a smart ass.
Yeah.
But
so Thales is to that donkey as academia is to me. It's trying to crush my spirit and think I'm an idiot, but really I'm the one doing. I'm the one doing all the work. Mm-hmm. So Thales is the father of geometry, roughly speaking. And I also wanted to get into that there are, how many Greek letters are there in the Greek alphabet? Currently 24, but there used to be 27. So the 3 that they're missing are called digamma, copa. There's a word with no U after the Q. And my favorite one, Sampi. Yeah, he's Gandalf's rune. He's that one. And Sampi's that one, and I'll give you the other one. Copa was this guy, kind of looked like Phi, but not quite. And then where's the other one? They also called it Copa.
Also not quite Kappa. Copa.
Copa, and then where's the digamma? I don't see it anymore. Just wait. Oh, digamma was like an F. Symbols you haven't recognized. But the reason they had this and why I point them out now is because they were attaching numbers. This was the same as where they get, I think I have this in here somewhere, but it was Nero de Vla. Nero was a narcissist and he was extremely mean, and he's where they get the number of the beast 666 from. His name in Hebrew gave you 666 because the Hebrew alphabet was also numbers, and so was the Greek alphabet originally. And this is what they're doing. So this would be the units, the tens, and the hundreds. And then so what they're doing is, so that would be powers of 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 9 times 3 is 27 letters in the alphabet that they had originally. So let's do this. We might as well go through. We'll learn a little bit about languages. Math is the language of the universe. These are just the substitutes. So when we get this, what they did was, I don't know which way they went, so they did go down. Can you do the alpha, beta, gamma? They're using lowercase, delta, epsilon. The digamma comes in here now, next. Digamma, yeah, we'll get there in a second. That one's zeta, eta, theta. Zeta, eta, theta, iota, kappa, lambda. I'll just look at each one. Lambda, mu, nu, xi. That was omicron, p, copa. And then rho. I'm not. There's a test at the end. So it's rho, sigma, tau. I'm gonna guess. Yeah. And then the one he wanted. Upsilon. Phi. Chi. Xi. I don't care. It's not. It's chi. Chi squared. Do you want to compute someone's inner chi or their chi? This is C. But I want to do that right now. Go to the Dr. Google and make him say, how do you pronounce this symbol? Fuck all of you. No. Omega. Just wait. Omega. And then see, that's why he was the beginning in alpha and omega. Not in the original alphabet. It was alpha and Sampi. Sampi was the last one. What'd you call me? Anyways, there's this original Greek alphabet in the, what is this? The Ionians. This would be the original, oh no, Hellenic period. Oh, the Ionians, I guess, yeah. And then, so just for reference, they got rid of, where are they now? This one for sure. And then Copa they got rid of. And then this one they got rid of. So those three got deleted. Then there was 24. 24 has way many more divisors than 27 does. We'll get into that some other time. But this was roughly in the 6th century BC, and then Thales and Pythagoras. But it's all the E sound, right? And then that's why they rhymed, because they're having the alphabet. So when it's Phi, Chi, Si, and mu, nu, zeta, theta, P, etc.
It's gonna be my favorite one. Zeta, eta, theta. What's a theta? Does it taste good? Zeta, eta, theta.
Zeta, eta, theta. Why was 6 afraid of 7? Because 7, 8, 9.
Because zeta, eta, theta.
Zeta, eta, theta. We can make 2 of those. Let's make one for every language. Oh, there's a French one. How do you say 3 cats drowning in French? Un, deux, trois, quatre, cinq. I got Tim with that one. Here's 13 books. You may have heard of them. They were called The Elements originally. Do you know why I own this copy? Nerd, yes. But before Mark Solomonovich wrote his tour de force on geometry, we were the guinea pigs. And I had to learn from the actual 13 elements. You can see where it's like broke down, and there's book 1 definitions, etc., etc., etc. So I also have the 13 elements. We're going to do a construction from there in a second. I don't know where to even wrangle it in when I talk about the Greeks, because this is the super great. So here's a quote from Pythagoras, and then we'll do a quote from one other dude. You'll probably recognize the dude when we get there. His name is Johannes Kepler. So here's Pythagoras. You could take it with a grain of salt if you want, because he also thought that farts were your soul seeping out of your body. So he literally banned beans and legumes from the cult. You weren't allowed to eat them. So I don't know. He had some stuff right, some stuff wrong. But I agree with this statement, not the first one. Reason is immortal. All else is mortal. Reason in the world today. Reason is the only thing that I will, adhere to. Oh, there's another one from Pythagoras. Where's that quote I wanted? I missed it. Oh, there's one from Thales. He's talking about traveling. Thales of Miletus. Oh, there it is. I'm not going to write it out because this one's a little bit longer. But this is Johannes Kepler. Geometry has two great treasures. One is the treasure of Pythagoras. The other is the division of a line into extreme and mean ratio. He's talking about the golden ratio. In Euclid's 13 Elements, he called it the extreme and mean ratio. It's extreme. It's not the average ratio. The average would be the average, the midpoint. What the one that we're going to construct is the one where we use the extreme and mean ratio. So it's extreme, but it's the average ratio such that when you cut, and I call this a unit length, whatever you're going to use, and I call this some length x, then what he's saying is the ratio to the whole thing, which would be x plus 1, over the ratio of this bigger guy must be equal to, on average, the larger guy to the unit. And then I think I've already used this once to show you in some other video that you can get the golden ratio from this, etc., etc. So this is what he's talking about. And then the first we may compare to the treasure of gold, and the second we may name a precious jewel, and this is by Johannes Kepler. So the two major things you should take out of there is a squared plus b squared equals c squared in any right triangle, and the other one is the golden ratio phi, which is equal to 1 plus root 5 over 2, and getting this construction. From the golden ratio, what I also wanted to talk about was if you cut that incorrectly and then make a square using straight edge and compass, using a circle, and then I do that, then every time I make this square, and then, I did it. How am I going to cheat if it's right on my hand right here, so I'm going to cheat a little bit, and then you can do this, and then you can do this, and then you can do this. And so there is a golden spiral in there. If you look at this, also, I really wanted to do that. Oh, this one will fit. It fit right in there. I need more hands. No, I'm just kidding. But
bring that a little close to the camera.
Bring it closer to I'm going to step on stuff. I don't know. This. How can I make it as awkward as possible? There you go. It fits right in there. We'll take a slow-mo video, but we have I have a whole bunch of them. I have bigger. That one won't fit, but it'll be the same ratio. And that was what I was going to talk about. Oh, bring that back. Where's the first one? Now I lost him. Whether it's the big one or the little one, that's not why I drew it for the spiral, actually. I baited you. Why I did it was because each one of these rectangles, the big rectangle and this rectangle and the little one and all these squares are now the same ratio. And so what the Greeks realized and what Da Vinci came along and the Italians when he was making his paintings in the Vitruvius Man, etc., with the dingleberries, there was no shame. There was no shame.
Yeah, I was not anticipating that.
You, that I would say dingleberry in the stream today? Dingleberries.
Dingleberry is not a word in a sentence that usually goes with the trivial man.
We're gonna start putting that on the Discord. Like,
can we make that like that's like a song title? Vitruvius Man and his dingleberry. Element. Now I forgot what I was talking about because all I can think of is dingleberry now. It's like you said it. It's like I know, but if I draw a person here, and then I draw a person here, they're the same ratio now because if I draw them at the same height in the box, I should have actually put them into the box the same way. There it is, he's got a long neck. That's a giraffe man. Giraffe man and his dingleberries. Where's his dingleberries? They're on his neck, clearly.
and immortalized.
It's like, you're live, right? It's like, this is what's inside my head. You have to see it too. What was my point? I can ruin art for you too, because in art, once you have the golden ratio and have a little bit of science in there and some mathematical logic and reason, you can make paintings which will immortalize you, or music which can be immortalized now because we can record it. But this is a vanishing point which preserves perspective. So anytime I draw the man in this square or further back in the painting, they'll be the same size because they're going to be the same proportion because they're the divine proportion. And so they use this a lot in art. And also when they would have a big Fresno like Michelangelo, when's it going to be done? When it's done. When it's done. He went blind doing this, but when a Fresno's on the wall that they're painting, and then it would sort of mean like, are you drunk today? It's like the painting is curving. It's like, what are they doing? They would use the golden spiral to correct the painting when it would go off, because it would just bring it back into this. So they would draw the golden spiral and then correct the painting by doing this. Also, at the Leaning Tower of Pisa, I love this. It's kind of tilted, so then the last piece they were like, well, we'll make it look straighter by adding the top. They realized that it was going down, and so they started building it to rectify this, but they're using the golden spiral to try and rectify this. All right, how much time we got? Because I'm just giving you the breakdown of what the Greeks were doing, and then eventually we'll do this. Oh, yeah. Oh, he's doing constructions, so I'm going to do a couple constructions and then end off, I guess, because then we're going to get into a whole bunch of other stuff. Have I done an hour today? Not really.
40 minutes.
Close enough. This'll fill up the time. So he has a bunch of basic constructions. I'll do 2 of them and see if I can do them. 3 of them? It doesn't really matter. 2 of them are roughly the same. Can you take a line and erect a perpendicular? I'm going to write it out because I get to say erect. And a perpendicular, not orthogonal, Tim. Erect a perpendicular. Yes, I can erect a perpendicular. 6 inches at a time. Erect a perpendicular to, it's like PC to a given line. I know, because I wanted to get that meme in there. Perpendicular, perpendicular. All right, what am I doing? Now I've drawn it where I don't actually have marks. Do I have a substitute? No. Martin Gardner. Martin Gardner, that's a good one. I was going to try and see if I actually had, well, I can use a straight edge, but Mark has an actual whiteboard compass. What you do is you take your segment. This is AB if you want. So if we're starting to do Euclidean geometry, this is where also the Pythagoreans didn't have any ideological caveats to where you weren't allowed in their club. The only caveat they had to be in their club was they had written on their big temples, let no one who does not know Euclidean geometry enter here. So their haves and have-nots were based strictly on whether you knew some Euclidean geometry. Women are allowed, men are allowed. I don't care where you put it. As long as you know some Euclidean geometry, you're in. You're in. I like that kind of cult. I like the one with the cat one. It's like, I don't know what religion this is, but sign me up. Yeah, they're holding the kitty. So then what we're going to do is, or to bisect the angle, is we're going to take, and then I won't prove it because I don't have that much time, and Mark's smarter than me, but he'll be like, you have to prove the construction after as well. So when we'll get into Mark's 4-step to where we analyze, and then we synthesize, and then we construct, and then we prove all these types of things. But what you want to do is take a radius larger than half, and then have it cut here, and then you want to move it to here and put the compass here and move it to half. So I'm doing like pseudo construction because I don't actually have the compass or the straight edge. And then I would use a straight edge, and then they intersect at some point, those 2 circles, and then I join those, and then that can construct. You're like, you didn't do it, because I was just like, I forgot what I was doing because I was talking and being a pedantic ass. I was thinking about erecting perpendiculars, but it did both. Because if you drop this guy and you join this one, if I call this C, if I drop this now, this will be a 90-degree angle. This will be 90 degrees. And also what we've done is roughly in the same construction is get the equilateral triangle. please point out in the comments, including Mark or whoever else, what I did wrong with that, and then we'll flesh out the actual constructions when I borrow his straight edge and compass, and we'll do it correctly. But this is the first thing that they wanted to do quite literally, and they're building pyramids and everything else from this. I have another method from the Mayans that used a bunch of knots and ropes to make sure that they can guarantee to get a right triangle, and then the rope stretchers had a much simpler one from the Egyptians, so we can compare and contrast these originally. But what they were doing was they had two allowable tools. The tools that they're using weren't the hammer and the saw. Theirs was a straight edge. This is different from what I knew a straight edge to be in high school. But one was a straight edge and the other was a compass. And this is for drawing circles. This one's for drawing straighty things. Straighty things, that's the term. And this one's for drawing roundy things. What are they what are they actually called? I'll tell the what Johnny joke. Can I tell a Johnny joke? No. Lorenzo? I'm telling it anyways. I'll censor. It's not that bad. If you had bigger tits, you'd be a 10. No, that's a urinate one. So Johnny and his friend are tobogganing down the hill, and they're like, "Do you think the wagon could down in the snow?" And they're like, "Let's try it." So then he runs the wagon down, and Johnny's friend falls out, and the handle goes up his ass, up his bum. I'm sorry. If we're talking about mules, I mean the donkey. It went up the donkey's donkey. So then Johnny goes back to school the next day. He's like, "Oh, I got a story for you, Mrs. Susan," or whatever her name is, Karen. Miss Karen. Susan Karen is her name. Immortalized. Susan Karen. Real piece of work. And he's like, so he tells the story. He's like, and then the handle went right up his ass. And she's like, "Wrecked him, Johnny, wrecked him." He's like, "Wrecked him, hell, damn near killed him." So why does that make me think of it? Straighty things are actually called rectilinear. I didn't spell that at all right. Brazil, rectilinear. And these ones are called curvilinear. But yeah, my dad still giggles when he tells that joke too. I've heard it 1,000 times, but he's not telling it for you. He's telling it for himself. Dad's wrecked him, hell damn near killed him. That's a urinate. I really got to go piss. Urinate, Johnny, urinate.
All these Johnny jokes.
Yeah.
They're all Johnny. It's all Johnny. It's all the same kid.
They're as old as the Greeks, I guess. And let's do one more. The extreme and mean ratio. Oh, I might need this. Do I remember how to do it now too? That's where it's like, can I just pull it out of the hat? We're going to get points A, B, C, D, E, F. And then at least I know I've done it right. So here's A, B, here's your original segment. And then now with a straight edge and a compass, what I want to do is erect, that's the terminology, erect a perpendicular to B. Then I want to cut off a circle of radius B on here. That will give me C. Then I'm going to join A and C with my straight edge. No, I don't know how to do it now. I forgot. I already forgot. Just wait. Is that in the right order? Luckily, secrets. Where is this? Not secrets. It's this one. Golden ratio. Don't open it in that one. Oh, I did. I'll get it. Don't worry. Yeah, the divine proportion. Here we go. Did I give me the constructions? Or did I leave myself? Oh, here it is. Just a second. I'm cheating. I wrote it out one time. There we go. Okay, wait. What did I do first? Okay. I was like, that shouldn't be C. That was correct. I'm just going to go back. First, you find the midpoint, C. How do we do that? What I just did. You construct, you drop it. It drops a perpendicular at the midpoint, a perpendicular bisector. Oh, that's what I forgot. Sorry, Mark. I was erecting a perpendicular bisector. Oh, there's some kind of entendre in there. I'm gonna leave it alone. It's like Lorenzo's like, thank Christ. In Italian though, he was thinking it in Italian. So there's C. Yay. Then I'm gonna, what do I do next, Adrian? Then I erect a perpendicular and I cut off, is it gonna be this? Yeah, this radius, half of the radius to B. So this is gonna be D. Then I'm gonna join A and D. Then what we're gonna do is on there, I'm going to bisect this segment now, the hypotenuse. How do you do that? You go out there, perpendicular bisector. There, we did it. Get out of the way, cat bug. I like that because I like ladybugs and cats, and they made a thing that was a cat bug. It makes me warm inside. So does erecting perpendiculars. And now I have that, that's E. And then we're in business. Then you draw a circle of radius E, and it will sect at F. And AF plus FB over AF is equal to AF over FB, also known as C,
Slick.
the golden ratio.
Very slick.
So in only a few steps of having to, I didn't even intend on doing that. Yes, I did. Erecting a perpendicular and perpendicular bisector, he uses that move twice. He erects a perpendicular here, and then all he's doing is erecting perpendiculars essentially, and using this to construct the golden ratio. Next time, or we'll get Mark in here somehow. Please, Mark, come down here and prove why that actually is the golden ratio and why this statement is true. Because I just did the construction, but then eventually you would have to prove in some rigorous manner that this actually was the golden ratio.
That would be
Also,
awesome
quick-
to have him as a guest lecturer.
Yeah. I'll
Fantastic.
convince him. He's also helping me with non-Euclidean geometry. So as a segue into there, I have to do a Zoom meeting at 2 o'clock, which is coming up real fast. And we're going to do non-Euclidean geometry. So just as a quick insight into this, can you see the orange? I don't know. Okay, well, just wait. Because then we'll do something, go Oilers. You can't really see that, so then we'll make it orange and blue.
There we go. So we have curved surfaces, basically, is what you're getting at, instead of flat surfaces.
And how do I know that there's only three varieties, is what I'm going to ask.
Ooh, very good.
Let's get one of Lorenzo's fancy pens. So, what does it mean to be a straight line? This is a straight line, and these are parallel straight lines in the plane. This great circle is a straight line, which is the biggest circle you can have on there because it has the radius of the actual sphere itself, the great circles. But if you look and I draw two great circles, can you draw two great circles on a sphere? There's two of them. Look at, they intersect. Those are parallel lines, but they intersect. So what's the definition of parallel and what's the definition of straight? And why is it that airplanes along these great circles and not in straight lines, that you're going to go along the arc? So why is the arc now what we call straight? What do we mean by straight? And what's the difference here? And it's like, well, frick, I'm teaching the class. I should probably rectify and know this right away. so, damn it. It's the shortest distance between 2 points. In the plane, it will be the straight line or the rectilinear line. But on here, that's why airplanes take those arcs. What they're doing is they're traveling in the geodesic of space-time. They're traveling in the shortest distance between 2 points is what we mean by straight. And so this is the epiphany that they had. And in Euclidean geometry, Mark will show you that if you have a triangle now, I switched from using your fancy one to just the black one again. But you can have a triangle on here, you can have a triangle on here, and you can have a triangle on here. Triangle meaning it has three angles. Willa, Kitty. She went to you guys and not me. How dare you, Kitty. But if you call this, okay, we can use the purple one, alpha, beta, gamma, the first three Greek letters, or alpha. Hey. Alpha, beta, gamma. There's trichotomy. The Neutral geometry has 4 axioms and or postulates, and the 5th postulate was the parallel postulate. And for thousands of years, they tried to say, can we derive the 5th postulate from the first 4 as a theorem and not an independent axiom? And the answer is no, because the sum of the interior angles on a triangle in the plane will also equal pi radians. So alpha, beta, gamma will equal a straight line. The sum of the interior angles in Euclidean geometry will always equal exactly pi radians. And that's equivalent to the parallel postulate in some mysterious way. And so now there's only 2 other choices. Pi can be equal to alpha plus beta plus gamma. Pi can be larger than alpha plus beta plus gamma, or pi can be less than alpha plus beta plus gamma. And there's a really good Veritasium video. No, it's not Veritasium, it's Veritas, just the truth. He has a channel and he talks about the flat earthers, and they're asking them just basic questions about geometry. And he says, if you have an equilateral triangle like the one I just constructed, what are the angles in the equilateral triangle? And he keeps trying to say that they're all pi over 2. But that means you would have 3 angles that are pi over 2 radians, which would be 270 degrees, which is crazy. But only in Euclidean geometry. You can get this on the sphere, and then you can get less. So this is what it's saying. If you have the parallel postulate and parallel lines never intersect, you know that you're in Euclidean geometry. If they do intersect, you've created another geometry and you're not in the right kind of geometry. And then when you go into the real world, you can't actually construct something that has exactly pi radians because no instrument is sharp enough. So what they're asking is, we're modeling the world with this guy currently because the Greeks have done it and Euclid did it with his 13 elements. He systematically did it. But it seems like Gauss was one of the first ones, but he was too worried, so he didn't publish it. This got published posthumously, but we're looking at the different kinds of geometries. I'm going to go do that in a Zoom meeting. If you want to join the Zoom meetings, you got to pay us. So please subscribe to our Patreon and do all these types of things. Eventually, we'll do this, but I'm doing an independent study class, and coincidentally, McEwen paid me $0 for it. So I'm just doing it just because I like geometry.
There we go. So thank you, viewers. Join us next time for more history of math when we discuss further constructions of Euclid and geometry. All right, thanks everyone. See you next time.